Alright, so okay, so let's sort of continue where we left off. So if you recall, last time I outlined the sort of meta strategy for proving lower bounds for algebraic circuits. The first step of this strategy is to do depth reduction, and that's what we discussed in the last talk. And once you are at a small depth circuit or formula, then you need techniques to prove lower bounds for such objects. Okay, and that's sort of the focus for of this talk. And so the answer, so the question is, can we prove lower bounds for small depth formula / circuits, the kinds that we get after a depth reduction? And the answer is yes, if you place some sort of restrictions on your algebraic models of computation. And that's what we're going to talk about in this talk. And the techniques here are mostly algebraic, right? So you saw the techniques in the depth reduction thing, there's just divide and conquer algorithm, so fairly combinatorial. Whereas here the techniques will be algebraic, typically based on some sort of linear algebra, matrix rank, and so on. And we use these kinds of techniques to prove these lower bounds. Okay. All right, so this is sort of the plan for the rest of the talk. So as I said, I'm not going to prove lower bounds for general ABPs / formulas, whatever. I'll prove lower bounds for restricted models. And these models are going to be restricted in different ways. So the first model I'll consider are non-commutative ABPs. This is again something that Christian briefly mentioned in the morning, and I'll go through it. And we look at Nissan's lower bound, again something that Christian briefly mentioned but didn't completely describe. Okay, and then I'm going to talk about homogeneous sigma pi sigma formulas. Yes?
So what restrictions does this depth reduction preserve? Like the ones we consider are all preserved?
Right. So that's a great question. So the question is, so if we when we do depth reduction, does it preserve all these criteria? And it turns out it preserves many of them. So for example, what I said about algebraic branching programs just carries through in the non-commutative setting without any changes. Similarly, homogeneity, multilinearity, many of these things are preserved. Yeah, but it's not always immediate. You have to go through the proof and check. Okay. Right. So the second thing we'll do is lower bounds for homogeneous sigma pi sigma formulas. Again, homogeneous I briefly described the last time, but I'll go through it again. And there's a lower bound due to Nissan and Wigderson. And then we'll discuss some extensions of the Nissan-Wigderson method for proving lower bounds. And I'll end with some open questions. Okay. So let's start with the non-commutative lower bound. Okay. So what are non-commutative polynomials? Let's just briefly recall. Right. So suppose I want to compute, the way we sort of motivated algebraic circuits were computational problems where your problem is that you want to compute a multivariate polynomial over elements that take values in some field. Okay. But now what if your elements don't take values in some field but in some sort of non-commutative domain? Right? So think, for example, about 2 by 2 matrices or things like that, where multiplication is not commutative, but it still makes sense to look at things like polynomials over that domain. Right? And if you're looking at things like this, well, then a polynomial will be a linear combination not of commuting monomials, right? Because matrix product doesn't commute, but your monomials are going to be more like ordered strings over your underlying alphabet of variables. Right? So, and now a polynomial will be a linear combination of such strings. So it will be a linear combination of such monomials. Okay. So that's what a non-commutative polynomial is. And I'll denote non-commutative polynomials by this sort of f bracket x1 to xn with this angular bracket. Okay. All right. So here's a simple example of a non-commutative polynomial. So suppose I have two variables x and y. I can look at the polynomial which is the sum of all length 4 palindromes, let's say over the alphabet xy, and then there are 4 length 4 palindromes, so you get like a nice degree 4 palindrome polynomial. Okay, so this is sort of a nice feature about the non-commutative setting is that if you have just two variables in the commutative setting, if you have a 2 variable polynomial of degree d, then you can have at most something like d squared monomials. But if you have a 2 variable non-commutative polynomial of degree d, then you can have 2 to the d many monomials. Okay, so sometimes in the non-commutative setting, even looking at polynomials with just 2 variables makes a lot of sense. Slightly different from the commutative setting. Okay. All right, so that's a nice example. Okay, so what do we know about the non-commutative setting? And so most of what I said in the last talk, there's a small caveat, but most of what I said works just without changes in the non-commutative setting. So for example, you can define the same complexity classes, formulas, algebraic branching programs, circuits. And again, you have the same inclusion relations. Formulas are at most as strong as algebraic branching programs, which are a subclass of circuits. Okay, and the nice thing about this is now you can ask your favorite question in the commutative setting in the non-commutative setting. Okay, so for example, you can ask, does the n by n permanent have polynomial sized non-commutative circuits? Okay, and this is related to a commutative circuit, the commutative question in a simple way. In particular, the lower bound question here is easier than the lower bound question in the commutative setting. Okay, so let me just say a little bit about that. But before I to make this question precise, you really have to first define what the n by n permanent means in the non-commutative setting. Yeah, we know what it means as a commutative polynomial. What is the n by n non-commutative permanent? Well, you can make this precise in any number of ways. You can take your favorite polynomial, for example, the permanent, and order every monomial as a string in some particular way. So for example, for the permanent polynomial, I've ordered each monomial sort of row-wise. And this gives you a non-commuting polynomial. It's this linear combination of strings, right? And now the question is, does this non-commutative polynomial have a small non-commutative circuit? Okay. And now having a non-commutative circuit for something is really, for example, for this polynomial, is a much stronger thing than having a commutative circuit, right? Just on intuitive level, having a non-commutative circuit for this polynomial allows me to compute this polynomial on non-commutative domains like 2 by 2 matrix algebra, something. So in particular, given an algorithm for computing this permanent over such non-commutative domains, I can of course compute them over commutative domains like 1 by 1 matrices, which is a special subcase, right? So in particular, I'd be able to compute the n by n commutative permanent. So in particular, having a non-commutative circuit implies that you have a commutative circuit, right? So upper bounds are much harder in the non-commutative setting. As a result, lower bounds should be, at least in theory, much easier. So it should be a formally easier question to prove lower bounds in the non-commutative setting than it is to prove in the commutative setting. Unfortunately, this is still in theory because these kinds of lower bounds are still open. So in fact, the best lower bounds we have in the non-commutative, for non-commutative circuits match the best lower bounds we have for commutative circuits. So we don't really gain anything, at least in the circuit setting.
So how about the upper bound? Is that 2 to the order n upper bound?
Right. So if you look at, yeah, absolutely. So you have non-commutative circuits of size 2 to the order n. In fact, you can say something more. We have non-commutative sigma pi sigma formulas of size 2 to the n for the n by n permanent. Right. Okay. All right. So the circuit question in the setting is still open, but it turns out that if you sort of set your sights a little bit lower, and instead of proving lower bounds for circuits, you ask for lower bounds of weaker models of computation, then we do have it. Okay. So for example, we know that the permanent does not have algebraic branching programs in the non-commutative setting, and the permanent, by permanent I mean the non-commutative permanent that I defined in the previous slide. So it's known that it does not have algebraic branching programs of polynomial size. In particular, any non-commutative ABP for the permanent must have at least 2 to the n size, so exponential size. Okay. So I want to outline a proof of this theorem. I won't prove it for the permanent, but I'll prove it for some other explicit polynomial, and the same ideas result in the lower bound for the permanent. Okay. All right, so let's begin the lower bound. And again, as I said, this lower bound follows this two-step process, right? The first step is a depth reduction. So now we're going to do depth reduction for algebraic branching programs, because that's the model for which we want to prove lower bounds, right? And I'm not going to use the full power of the depth reduction statement. I'm just going to use what I call the basic identity. Okay, and the basic identity was the following. If you have an algebraic branching program computing a polynomial of degree d, a small algebraic branching program, then it can be written as a small sum, where each term in the sum is the product of two polynomials of degree at most d over 2, much smaller degree. Okay, and this is sort of the basic identity we used in doing the depth reduction, and it turns out that this is enough to prove lower bounds for non-commutative ABPs. Okay, so this is the thing that we sort of observed in the last thing, and so I'll need just a slight refinement of this, which is that if I start with an algebraic branching program that computes a homogeneous polynomial of degree d, right? A homogeneous polynomial is one where all the monomials have the same degree. If I have a homogeneous polynomial of degree d, then I get the same kind of decomposition, but in addition I have that these polynomials are all homogeneous. They're all homogeneous of degree d by 2. Okay, and now this version, the homogeneous basic identity, is enough for me to prove lower bounds. Yeah, and the way we're going to prove lower bounds is we're going to come up with an explicit polynomial for which any decomposition of this form must have large size, and that immediately implies the lower bound. Okay. Any questions about this basic strategy?
So the homogenization step for MEP is the same as before?
Yeah, it's exactly the same. Right. Exactly, it's the same. Right. So, good. So how are we going to go about proving this lower bound? So the way we're going to do it is by defining a kind of an algebraic complexity measure. Okay. So what we're going to do is take any polynomial which is homogeneous and degree d and define a notion of complexity for it. So it's going to be algebraically defined, but it's a number. So a complexity mu of f. Yeah, and this complexity has the definition that we're going to give. It has some nice properties. The first property is that it's small for any term in this summation, right? So you have a sum of terms. Each term has small complexity. Yeah. The complexity is subadditive, right? So if I add together two terms of small complexity, I get something else of small complexity. And finally, I can find an explicit polynomial such that, this should be mu of f. I can find an explicit polynomial f such that mu of f is large. Okay. So we will define a complexity mu of f for any polynomial f which has these three nice properties. Each term has small complexity. The complexity is subadditive, which means a sum of a small number of such terms has small complexity. But then we can easily find f such that this complexity is large, which means that any ABP for such an f must be large. Okay. So how do we go about defining this complexity measure? So it's extremely simple. It's basically based on matrix rank in a reasonably obvious way. Okay. So let's do it. So suppose I have a polynomial f homogeneous of degree d. Then I can write it as a linear combination of monomials. So recall that a monomial is just a string for me. So these are just strings of length d over the alphabet x1 to xm. So these are strings of length d. And each monomial m has a coefficient which I'm calling cm with a subscript f. Yeah. So what we do in order to define this notion of complexity is that we look at a certain matrix associated with this polynomial. And how is this matrix defined? So this matrix is really big. The rows and columns of this matrix are sort of labeled by monomials of degree d over 2, right? So I take every monomial of degree d over 2, so every string of length d over 2 over this alphabet of size n, and for every string there's a row in this matrix, and similarly for every monomial m2 of degree d over 2 there's a column, okay? So it's an n to the d by 2 by an n to the d by 2 sized matrix, and now the entry corresponding to row m1 and the column m2 is the coefficient of the product monomial m1 times m2 in my polynomial f. Okay, so okay. Yeah, does the definition make sense? Okay, I have an example here. Yeah. So let's take the palindrome polynomial that we defined a few slides ago, right? And so what's the corresponding matrix here? So it's a polynomial of degree 4, right, over two variables. So I have a 4 by 4 matrix, right? The rows are labeled by monomials of degree 2, columns by monomials of degree 2, and I put 1s or 0s depending on the coefficients. All coefficients are 1s or 0s here. So I put 1s or 0s depending on what the coefficient is. Right? So you get some nice 4 by 4 matrix. In this case, it turns out to be a permutation matrix. Okay. So we define this matrix for any polynomial f, and what we do is we define the complexity of f to be the rank of this matrix. Okay, so if we take this big matrix, we look at the rank of this matrix, and that's my notion of complexity. Okay, so let's just quickly check that it satisfies all the nice properties that we were talking about. The first was that each summand in the sort of basic identity has small complexity. And the reason for that is extremely simple. So suppose I take a summand of this form, f is the product of two homogeneous polynomials of degree d over 2. Now, if I look at the coefficient of m1 times m2 in f, right? This is where non-commutativity really enters the picture here. If I look at the coefficient of m1 times m2 in f, well, m1 times m2 sort of factors as a product of two degree d by 2 monomials in exactly one way, right? So you can only factor it as m1 times m2 and not as m3 times m4 for some other m3 and m4, right? So that means the coefficient of m1 times m2 in f is the coefficient of m1 in p times the coefficient of m2 in q, okay? And that immediately implies that the rank of this matrix is at most 1, which means its complexity is at most 1. Okay? Right? So this is out of the first property we wanted. We wanted a notion of complexity such that every term in the basic identity on the right hand side has small complexity. And this is as small as it gets. So the rank is at most 1. So that's really tiny complexity. Okay? All right, so that's the first property. The second property was that this complexity measure is subadditive, right? I want the complexity of f plus g to be at most the complexity of f plus the complexity of g. And this is immediate from the definition of matrix rank, right? The way I've defined this matrix for a given polynomial f, the matrix corresponding to the sum of two polynomials is the sum of the corresponding matrices for each polynomial, right? So m of f plus g is just m of f plus m of g. So the rank being a nice sort of subadditive function, that will tell you that the notion of complexity that we have is subadditive. So the rank of m of f plus g is at most the rank of m of f plus the rank of f of g. So the complexity of f of g, f plus g, is at most the complexity of f plus the complexity of g. Okay, so this is usually subadditivity. Whenever we use sort of matrix rank to define a notion of complexity, subadditivity always sort of comes for free because of this. Okay. All right, so that's about it. So we are ready to prove our lower bound. So suppose I have some ABP of size s computing a homogeneous polynomial of degree d. It has this decomposition given by the basic identity. And so what I know is that the rank of the matrix corresponding to the ABP A is going to be at most the sum of the ranks corresponding to matrices corresponding to each of these terms, right? And each of these terms has rank at most 1. So the overall rank adds up at most to the size of the ABP, which is S. Okay? Right, so just think about this. I have this massive matrix. It's an n to the d by 2 cross n to the d by 2 matrix. So it's a really big matrix. And suppose I had a polynomial sized ABP. I'm saying that this huge matrix has rank polynomial, right, which is really, really tiny. So I'm saying something very, very strong about polynomials that have small ABPs. Okay? So that's about it. So now, yes, question? Okay.
So you can just define the measure to be the minimal A such that you can write A in this form.
Right.
In this case, it turns out to be the rank.
Absolutely. In this case, actually, this is, yeah, completely right. It's equal to the rank. That's right. But this will not always be the case.
Yes.
Okay.
Right.
Okay, good. And right, so that's it. So that more or less finishes the lower bound. All we have to do is now find an explicit f for which this measure is not small, and then we are done. So that means all we need to do is find an f such that when we write down this big matrix for it, it has large rank, super polynomial rank, but we can easily cook up f for which it's in fact full rank, and so that yields an exponential lower bound. Right? So for example, you can take the degree d version of the palindrome polynomial that we're talking about. Yes, question.
So what goes wrong for circuits? You have similar decomposition result for circuits you mentioned in the last part of the talk.
Okay, so good, great question. So I'll just get to that maybe after this one. Right. So to prove a lower bound for explicit f, so what we do is we just take something like the degree d palindrome polynomial, and exactly analogous to the degree 4 case that we wrote down, if you write down the same matrix for the degree d palindrome polynomial, you end up with a permutation matrix. So there's one exactly 1 1 in every row and column, and otherwise 0. So it's a full rank matrix. Okay, so the complexity of such an f turns out to be 2 to the d over 2, because I have two variables, and so it's 2 to the d over 2. So as large as possible. So this immediately implies that any ABP computing, let's say, the palindrome polynomial of degree d must have size at least 2 to the d over 2. Okay.
Is it possible to show that for cumulative no such measure exists, mapping those products into something smaller, which is
right. So it's not possible to say. So no, as in it depends really on the complexity of the measure, because as Avishai was saying, you can always define it to be the smallest s for which it exists. It's just that it would not. I don't know if you would get anywhere with that. Right. So yeah, you can always define a measure which is the smallest s such that you have such a decomposition, and in principle that's enough to prove lower bounds. But
so would the measure be small for the products?
Right. The way of suppose you define your measure to be the smallest s such that there is such a decomposition, then the measure of every product is 1, and you have all these nice properties. It's just that we don't know how to find an explicit f for which that measure is large.
So where have we used the non-commutativity?
Yeah, so the non-commutativity was used in this statement, because so what you are really using here is that the coefficient of m1 times m2 in f is the coefficient of m1 in p times the coefficient of m2 in q. And that's because of non-commutativity. Okay, so it's a rank 1 matrix because it's non-commutative. It's not in general rank 1. Okay.
Is there any hope of showing a 2 to the d low bound for this one?
So, so it's 2 to the d. Sorry.
But the answer is this is the complex answer.
Yeah, it's the complex.
This is tight, right?
This is tight.
D times to the original.
Yeah.
Sorry, what was the question?
So question is, can you prove a lower bound of 2 to the d instead of 2 to the d over 2 for a degree d polynomial? Right. So this is really about so it's really about when we are measuring ABP size. Are we talking about vertices or edges? Maybe because in terms of vertices, this bound is tight in the sense that it's the largest that it can be for anything. But right, if you measure size in terms of edges, then it's conceivable that you can get 2 to the d. But I'm not sure of such a result. Right.
But this is because you only have 2 different variables, right? X and Y. If you picked n variables, then
Right, you'd still get like an n to the d over 2.
Yeah.
But then the question still stands: can you prove an n to the d lower bound? And right, and then you would get the same. Yeah.
If you do the determinant, I think you can get, for every layer, you get something really nice.
Right, but that's going to be much smaller than n to the n. It's the bound for a determinant is like 2 to the n, and
I think you get this. I think you get something, but I don't remember.
okay, all right, okay. Yeah.
You also use non-commutativity in just encoding the polynomial as a matrix, right? There's no natural way to view the monomials arranged as a matrix.
No, well, this definition definitely makes sense in the commutative setting, right? I can just say, oh, take every monomial degree d over 2, take every monomial degree d over 2, and put the coefficient of the product in the corresponding entry.
There are multiple.
There would be multiple things that correspond to the same sort of monomial. Yeah, so it's not as neat a definition, but the definition still makes sense. Yeah. But you're right. I mean, the fact that each entry corresponds to a unique monomial is what makes it work in the non-commutative setting. Okay. So, right, so that's the lower bound. So, just before I continue, Rahul asked this question about why doesn't this work for non-commutative circuits? And the reason for that is that the sort of basic identity I wrote down for non-commutative circuits in the last talk, that doesn't quite pan out in the I wrote down a basic identity for commutative circuits. That doesn't quite pan out in a non-commutative setting. In fact, in the non-commutative setting, there is no depth reduction for circuits. There is a depth reduction for ABPs, there's a depth reduction for formulas, but for circuits it breaks down. Yeah. In fact, the palindrome polynomial here, it actually has a non-commutative circuit, but nothing of small depth. All right. Any other questions? Okay. All right. So now let's go back to the commutative setting. So, all right. So, so what we want to do is sort of port these kinds of bounds to the commutative setting. Okay. And at least one strategy might be to just look at the basic identity and again try this kind of argument. We don't know how to make it work. Okay. But you can sort of go further. This is not the only sort of depth reduction statement we proved in the last talk. We proved others, right? And so if you recall, I said that we can reduce to depth 4 by blowing up the size a little bit. Okay, and just recall the statement of that and try to motivate what comes next. So what we showed in the last hour was that if you start with an AVP, which computes a circuit of size S and a polynomial degree D, it's not just that you can write it down as a sum, as a small sum of products of pairs of polynomials. You can also write it down as a small sum, as a product of many more than just a pair of polynomials, many polynomials, each of small degree. Okay, so you can do this, and you can do it in a way where the blow up is not too much. Okay, so I don't want to get into what these numbers were from the last hour, but this S prime was not much larger than S. It was super polynomial, but it was not like a trivial blow up. Okay. the result of this kind of depth reduction was that if you can prove non-trivial lower bounds for these kinds of objects, so in particular if you can show that a polynomial has the property that any such decomposition as a sum of many products of many small degree polynomials must be large, then in fact you've shown a lower bound for ABPs. Okay. So this seems at least inherently an easier model to deal with than this one, right? Because this is just a product of two polynomials. This is a product of many polynomials of small degree. You can always convert a product of many polynomials into a product of two polynomials because you can just break them into two buckets, but it's not clear how to go the other way. So this is definitely a stronger decomposition, right? And you can hope to use this in order to prove lower bounds for ABPs. Okay. So can we, right? And that's the question. So can we prove lower bounds? Okay, so we don't know how to use the basic identity to prove lower bounds. Can we use the slightly souped up version of the basic identity to prove lower bounds? Okay, can we prove lower bounds for these kinds of formulas? And in particular, can we prove strong enough lower bounds that will allow us to infer lower bounds on general ABPs? Okay. And so this is what's going to motivate what I'll talk about next. But the short answer is we can prove lower bounds for these kinds of objects, but the kinds of lower bounds we prove fall exactly short of proving super polynomial lower bounds for general ABPs. Okay, so we can prove something, but not to the extent that we can prove super polynomial ABP lower bounds. Okay, so it actually falls just short of that. So I hope that made sense. Is it okay? Okay, so let's go ahead with proving lower bounds for homogeneous sigma pi formulas. Okay, and instead of actually dealing with that more complicated model, I'll actually deal with try to prove lower bounds for an even simpler model, which are homogeneous sigma pi sigma formulas. So what are these? So just recall that a formula is said to be sigma pi sigma if it's a sum of product of linear functions, right? That's what a sigma pi sigma formula is. And I'm only going to deal with homogeneous sigma pi sigma formulas. So homogeneous sigma pi sigma formulas are essentially sigma pi sigma formulas that never compute polynomials of degree larger than necessary, right? So if I'm computing a polynomial of degree d, I'm going to be looking at a sum of terms, each of which computes a polynomial of degree d, right? So it's going to be a product of at most d linear functions. Okay, that's how I define a homogeneous sigma pi sigma formula. Okay, it's an even weaker model that's sort of interesting. And this is related to what Christian was speaking about in the morning, where instead of allowing these products to involve different linear polynomials, you just force them to be the power of the same linear polynomial, right? So it's just a sum of powers of a linear polynomial. Okay, and I'll call this a sigma power sigma formula. Okay, so it's denoted in this funny way with a sort of a wedge between two sigmas. So sigma power sigma formula is just a sum of powers of linear polynomials. Okay, right? And so just to connect up with what Christian was saying in the morning, the smallest s such that some polynomial has a description of this form is the Waring rank of that polynomial. Okay, so the complexity in this model is closely related to Waring rank. Okay, so just to recall, we want to prove lower bounds for sigma pi formulas, but instead I'm going to prove lower bounds for these weaker objects and then tell you a little bit about how to do the other thing. Okay, alright, so there's an interesting thing though when you look at this sigma power sigma formulas is that it's not clear that every polynomial has such a representation, right? So usually when we do complexity theory, we're dealing with complete models of computation and then you want to prove lower bounds for some explicit polynomial. But it's not even clear that every polynomial can be written as a sum of powers of linear functions. So for example, the polynomial x1, x2, it's not clear that it can be written as a sum of powers of linear functions. But in fact it can, and this was explicitly pointed out in this result of Spielka from 2001, that any polynomial has a sigma power sigma formula of exponential size. So the upper bounds are given an exponential, but in principle every polynomial can be computed this way. Okay. And the way to prove this is via this thing called Fisher's identity that Christian pointed out in the morning. Right. Any questions about this? Okay, so we want to prove lower bounds for sigma pi sigma and sigma power sigma formulas. So how do we go about doing it? Right? And again, the idea is the same, right? So Here there is no really depth reduction because the depth is already small, so there's no depth reduction. So it's just the second step that we have to do. Okay, and what's the second step? Again, we define this complexity measure for polynomials, right? And we want to do it in a way so that the complexity of each term in the sum is small and the complexity is subadditive. Okay, and finally we'll find a polynomial for which the complexity is large, and that will give us the lower bound. So what's the complexity in this case? It turns out to be a rank, again the rank of a matrix, and it's the rank of the so-called partial derivative matrix, which I'll define on the next slide. Okay, so so Nissan and Wigderson defined this very nice notion of a partial derivative matrix. It turns out the rank of the partial derivative matrix will be the right complexity measure to use in this setting. And so this is a pretty important technique in algebraic complexity because it's sort of been built upon and it's been used in many different ways to prove lower bounds. So something worth knowing. It's also known that Nissan and Wigderson are not the first people to define this. So Sylvester back in 1851 apparently looked at some version of this. So it's known from slightly some time before, but okay, so we'll look at the Nissan-Wigderson definition. All right, so just to motivate this definition of a partial derivative matrix, right, let's go back to Nissan's measure from the non-commutative lower bound and sort of see why partial derivatives might be useful in this context. So if you recall, we had this sort of matrix definition for the complexity of a non-commutative polynomial. And this is how it worked, for example, for the palindrome polynomial of degree 4. Okay, so suppose we want to define an analogous complexity measure for commutative polynomials. How would we go about doing it? One way to do it is to see what this measure means on some related commutative polynomial, right? And sort of get intuition from that. So how would we think of f of xy, this palindrome polynomial, as a commutative polynomial? So how would we think of it? Well, one way is to simply let all the variables commute. That's the obvious way. But when you're doing that, you're somehow losing information, right? You're losing information about where the positions of various variables, so you're somehow losing information if you're allowing variables to commute. So an alternate, nicer thing to do is to sort of tag every variable with the position that it appears in. Okay? So in a non-commuting monomial, a monomial is a string. So a variable appearing in the monomial carries two kinds of information, the variable itself and the position that it appears in. And if you sort of tag the variable with this position and then you allow things to commute, you really are preserving all the information in the polynomial. Okay, so a natural thing to do is maybe look at the following polynomial. So you just take the same thing, but now you make 4 copies of the x variables, x1 to x4, and 4 copies of the y variables, y1 to y4. And now instead of looking at x times x times x times x, you look at x1 times x2 times x3 times x4. The content being that you have an x at position 1 times an x at position 2, etc., etc. And now if you think of this as a commutative polynomial, as a commuting polynomial, you've not really lost any information. You can sort of read off the non-commutative polynomial from it. Right? So it's a nice way of sort of translating from the non-commutative to a commutative setting. And the good thing about looking at things this way is that partial derivatives very naturally start appearing when you look at Nissan's measure. Okay? So for example, if I look at the partial derivative of this polynomial corresponding to the variables x1 and x2, right? So just some basic calculus will tell you that the partial derivative corresponding to x1 and x2 is essentially the sum of all those terms that contain x1 and x2, right? So that's, I'm writing it sort of in a verbose way, but it's really it's just x3 times x4, but I'm writing it as 1 times x3 x4 plus 0 times x3 y4 plus other things. Okay? So this is exactly the first row of my matrix, right? So one way of sort of interpreting the matrix, the coefficient matrix that we use to define Nissan's measure is that the rows of this matrix are just partial derivatives of this polynomial corresponding to variables that appear in positions 1 and 2. Okay? And so this is, so it's kind of natural to see where partial derivatives appear here. And it's sort of this kind of idea we're trying to lift to general polynomials in the commutative setting. Okay. Yeah, so it's some vague intuition. It's not very precise, but I hope this gives you some feeling for why partial derivatives are necessary and important. There's also some sort of geometric intuition, but I don't have it. So, yeah. Okay. So, all right. So let's go ahead and define this partial derivative measure. Okay. So now I'm given a polynomial f in x1 to xn. It's a commuting polynomial. And I want to define my complexity of this polynomial. And in order to do this, again, I'm going to define this big matrix. And, okay? And now the rows of my matrix are going to be partial derivatives of my polynomial. Okay, so I take my polynomial f and I look at all kth order partial derivatives of f, yeah, for some k. So k is going to be a parameter that we'll choose to our advantage. So k, fix some k and take all partial derivatives of order k. Okay, so here I'm taking partial derivatives with respect to distinct variables. Doesn't have to be that way, but just for simplicity, let's take distinct variables here. So I take all partial derivatives of f with respect to k distinct variables, and that gives me a set of polynomials, right? I get a large set of polynomials. So for every possible set of k variables, I get a polynomial, right? And now I write down this giant matrix where the rows of this matrix are labeled by k sets of variables, the sets of variables with respect to which I take the partial derivative. And the row corresponding to x1 to xk is the polynomial which is obtained by taking derivative with respect to x1 to xk. Right? I take this polynomial, I write it down as a list of coefficients, right? So suppose I start with a degree d polynomial, this would be a degree d minus k polynomial. So it has one coefficient for every monomial of degree at most d minus k. So I write down this list of coefficients, and that gives me, when I write down for the whole thing, that gives me the partial derivative matrix. Okay. Right, so hope the definition is clear. And finally, the complexity of my polynomial is again the rank of this partial derivative. Okay, so just go through a small example. Right, so yeah, a small thing is that I can also write this as, so I can write this as the rank of the matrix, but I can also write it as the dimension of the span of the rows. That's sort of a nice short form for it, and it will be useful later. Okay. Alright, so let's just do a small example. So for example, let's say your polynomial was the very simple polynomial, which is just the product of all the variables, x1 to xn, right? So now what's the partial derivative matrix? Well, when I take derivative with respect to some k variables, maybe xi1 through xik, then what I'm going to do is essentially divide by those variables, right? So what I'm going to be left with is the product of the remaining variables, right? It's the product of the remaining variables. So when I take derivative with respect to xi1 through xik, I get product of all those xj where j does not lie in the set i1 through ik, right? So now every row of this matrix is going to have a single one and is going to be entirely zero otherwise, right? And each row has a 1 in a different position, right? Because from the derivative, you can easily sort of read off the variables that you derived with respect to, right? So each row has a single 1, and different rows have 1s in different positions. So this is again going to be a full rank matrix. The rows are going to be all linearly independent. So it's going to be a full row rank matrix, yeah? So the rank of this polynomial is going to be n choose k, which is the number of rows in this matrix. Okay. Yeah. All right, good. Okay, so that's a sort of simple example, and now, but you can do it for other things. Okay, so that's it. So that's our complexity measure, and now let's use it to prove lower bounds again. Okay, so again, our model of computation is that we are taking sums of powers of linear functions. And now we want to prove that our complexity measure has the right properties, right? The properties we want to prove are that each term in the sum has small complexity and that the complexity measure is subadditive, right? Subadditivity again follows from the fact that this is a rank measure and rank is subadditive, so there's nothing to prove there. The non-trivial thing to prove here is that each term in this expansion has small complexity, and that's again something very, very easy to prove. So I claim that each power of a linear function has complexity at most 1, and that's just elementary calculus if you think about it. So if you take the kth order derivative of a linear polynomial raised to the power d, right? Doesn't matter which variables you take the derivative with respect to, you're going to get the same thing up to a constant, right? So every time you derive with respect to a variable, sort of shave off a linear function and you get a new constant. So in general, you get a product of these constants times a lower power of the same linear function.
This is one Li is homogeneous.
Right. No, it doesn't need to be, right? I mean, what are you going to do? I mean, even if it's not, it's true, I think. So, I mean, you can't derive the constant in any case, so.
Okay, so it's here 0.
Yeah, that's right. All right. Okay, so, so the important thing is that every derivative, right? So the derivatives, I have n choose k distinct derivatives, but all these derivatives are scalar multiples of the same thing, right? Which means that all the rows in my matrix are the same up to scalar multiplication, which means that this matrix has rank 1, right? So this matrix has rank at most 1. And then by subadditivity, my formula, which is a sum of at most s such terms, has rank at most s. Okay, so that's the sort of nice property we have from this complexity measure. All right, great. And so now, in order to prove a lower bound, all we have to do is find some explicit polynomial which has large measure. And this is something we've already done, right? So we said take the monomial x1 to xn. The partial derivative matrix of this monomial has all distinct rows, right? And not just distinct rows, linearly independent rows. And therefore, its rank is something like n choose k, the number of rows in this matrix. And therefore, what this means is that any sort of decomposition of the monomial of the form listed above is going to have size at least n choose k. Right? Yes?
I just want to make a point with regard to Christian's talk in the morning in terms of border warring ranks. So one critically strong version of the question that he asked this morning is a converse to the first implication. To say that if f has small rank under this measure, is it true that f has a small sum of linear powers, sum of powers of linear form?
Okay.
Just in the sense that that might be more concrete than the general border rank setting.
Right, but didn't he ask, but this is not a characterization of whether this has small complexity.
I mean, partial converse, so it's like,
partial converse.
It's maybe s on the left-hand side is a little bit larger than s on the right-hand side.
Right, right.
You can also see that the blow-up in this formula should be exponential, right? Because you can take k to be n over 2.
Right, exactly. So right. So now k is a parameter that we can choose as we want, and so we can take k equals n over 2. That gives us the best bound, and so we'll get that any such decomposition for the monomial must have size at least n choose n over 2, almost 2 to the n, and 2 to the n is roughly the right answer. In fact, 2 to the n is the right answer. So Christian he wrote down this identity in the morning that he called Fisher's identity, and that shows that in fact the monomial x1 to xn does have such a decomposition with 2 to the n minus 1 terms. Okay, and this gives an almost matching lower bound.
Can you improve the lower bound?
Yeah, so I think it's known that 2 to the n minus 1 is tight, but not via this technique. Okay, so all right, so that's it for sigma power sigma formulas. Let me also tell you a little bit about sigma pi sigma formulas, which is sort of a stronger model of computation. And it turns out that more or less the same ideas prove lower bounds even here. Okay, so again, our complexity measure is going to be the same thing. We're just going to take partial derivative matrices with respect to k partial derivatives. Okay, but this time the computations are a little bit different. Okay, so previously we had that each term has complexity at most 1. This time the complexity is not 1, but it's a not very large number. Okay, it turns out to be something like d choose k. Okay, and now d choose k might be pretty large, but you notice that it has no dependence on n. So if you think of d and k as somewhat smaller than n, this is much smaller than n choose k, which is the maximum rank of this matrix. Okay, so you can do this, and then again you can show that by subadditivity that the complexity of this entire formula is at most s times d choose k. Okay, and you can use this now to derive explicit lower bounds for sigma pi sigma homogeneous formulas. Okay, and in order to do that, you'll have to come up with some polynomial for which this complexity is again very large, right? We did it for the monomial of degree n, but now I want a polynomial of degree d for which this is very large, so it's going to be a slightly different question, and you can do this, right? So here's a simple polynomial for which this can be done. So this is the so-called elementary symmetric polynomial of degree d. So it's the polynomial where you sum all terms of degree d that contain at most one occurrence of every variable. Okay, so you sum all monomials of degree d that contain at most one occurrence of every variable. So it's called the elementary symmetric polynomial of degree d, and its so partial derivative matrix is very easy to analyze because, well, what's it going to look like, right? So when you take derivatives of this polynomial with respect to k variables, what's going to happen is that all the terms that contain all these k variables are going to survive, and they're going to be divided by these k variables, and all the terms that don't contain any of these variables are sort of going to become 0. Okay, so you're going to end up with a polynomial of degree d minus k, And what that polynomial is going to correspond to is essentially the sum of all monomials of degree d minus k that don't intersect with the set of variables that you took the derivative with respect to. Okay, so if you took the derivative with respect to x1, these sets should not contain x1 and so on. So what you're going to get, this matrix, what it's going to look like is it's going to be a 0, 1 matrix. The rows of this matrix are indexed by sets of size k, which are the sets of variables with respect to which you took a derivative. The columns are indexed by sets of size d minus k, and you're going to have a 1 if and only if the corresponding sets are disjoint from each other. Okay. So this matrix actually appears quite a bit in combinatorics and also theory CS and other places. It's called the so-called disjointness matrix, and the rank of this matrix has been investigated by a lot of people, and it's known that, for example, if you're working over characteristic 0 and k is suitably related to d, then this matrix is indeed full rank. Okay, and so you can just plug this fact in and derive your lower bound. So any questions at all about sigma pi sigma lower bounds? Or okay, so great. So okay, so let's finally get to yeah.
What do you say when you have sums of powers where the powers are not the same?
So it's the same. The argument is the same. You still get the same lower bound. I really didn't use the fact that the powers were all d in that setting, but I do use it here. Here I need that the degrees are at most d. But in the previous, the sigma power sigma lower bound, the exponents could really be arbitrary. Doesn't matter. Okay. All right. So what have we done? Right. So I wanted to prove lower bounds for general commutative ABPs. I said, okay, proving lower bounds for general commutative ABPs reduces to proving lower bounds for sigma pi formulas with some nice restrictions. I said, okay, before we do that, maybe we should do sigma pi sigma formulas first, and now we've done that. So now we should probably go back to sigma pi and see what can be done. And it turns out, so this is the question. So suppose I want to prove lower bounds not for sigma pi sigma, but homogeneous sigma pi, what can I do? It turns out that the partial derivative method no longer works. Okay, so that's the first thing. And even if you extend the model a little bit from sums of products of linear functions to sums of products of quadratics, already the partial derivative method breaks down and you cannot prove lower bounds. And this was a sticking point for a while until sort of a breakthrough result by Kayal in 2012, where he augmented the method of partial derivatives and invented the so-called shifted partial derivative method for proving lower bounds. And it turns out that this technique can actually be used to prove lower bounds for sigma pi. Okay, so let me just, I'm not going to do the computation in this case because it gets very hairy, but I'll just tell you what the complexity measure here is and tell you what bounds we can prove. Okay, and then I'm more or less done. All right, so in the partial derivative matrix, all we do is we look at the space of partial derivatives and we try to measure its rank. Okay, now what we do is that we augment this space a little bit in the sense that we start with the space of partial derivatives, but we sort of shift them by multiplying them with monomials of some degree. Okay, so you take your partial derivatives and you multiply them with monomials of degree at most L. Okay, and here L is some parameter. Okay, so you're looking at every partial derivative, you're looking at every monomial of degree at most L, you're multiplying them together and getting a large finite set of polynomials. Yeah, and these are going to be the rows of your matrix. Okay. Alternately, you can just define the complexity of your polynomial to be the dimension of the span of this set of vectors. Yeah? Does it make sense? Right? So if I take L equals 0 and I don't shift by anything, then I get the partial derivative measure, but for larger L, I get a different object. And this is the thing that we study. Okay? And again, subadditivity is easy, but it's non-trivial to prove that the complexity of each term is small, and the definition of what is small and etc. gets a little technically complicated. Okay, so but let me just give you a little bit of intuition for why such a thing might be useful. Okay, so at least that this has some sort of content, otherwise it just looks like a trick. So it turns out that this the space of shifted partial derivatives, this particular space has some sort of at least it measures something that's algebraically nice. Okay, and what is that thing? So just recall that if I have a collection of polynomials, right? If I have a collection of polynomials, I can talk about the ideal generated by those polynomials, right? And the ideal generated by those polynomials, so this is just from algebra. So suppose I have, I don't know, f1, f2 in fx1 to xn. The ideal generated by f1 and f2, this is all those polynomials that can be written as f1 times p1 plus f2 times p2, where p1 and p2 are arbitrary polynomials. Right, so that's the ideal generated by f1 and f2. And now this, of course, can be written as a linear combination. Every polynomial is a linear combination of monomials, so this can be written as a linear combination of things like f1 times a monomial, right? And similarly, the second term can be written as a linear combination of f2 times a monomial. Okay, so the ideal generated by f1 and f2 is in the span of the shifts of f1 and f2, right? Because f1 times m is exactly what you get when you shift f1. Similarly, shift f2. So in general, the ideal generated by the kth order partial derivatives of f is exactly things which are in the span of all shifts of the kth order partial derivatives of f, with no bound on the degrees of these shifts. Okay. So the ideal is this infinite dimensional vector space. It's spanned by this infinite set of vectors with no bound on the degrees of n. Okay. And now what we are trying to do is sort of measure the size of this ideal. Right. The size of this ideal has some sort of algebraic content, some geometric content, etc. We're trying to measure the size of this ideal, but how do we measure the size of an infinite dimensional vector space? Well, I don't know any way to do it. So what we do is we sort of take slices of this vector space and we measure the dimension of that. And that's what we do when we sort of restrict the degrees of these monomials. Okay, so sort of what we are trying to do is measure the size of this ideal, and the size of this ideal has something to do, some sort of captures some nice algebraic / geometric property, and that's what we are trying to do, and that's the motivation behind defining things this way. Okay, and okay, so now you can do this and you can prove interesting results. So I don't have much time, so I'll just quickly breeze through two, but I won't spend too much time. So the first thing is that the bound that we proved for sums of powers of linear functions, we can recover a similar bound for sums of powers of higher degree polynomials. Okay, so not just sums of powers of linear function, but sums of powers of higher degree polynomials. So that's something we can prove this way. Sort of more relevantly to algebraic circuit complexity, what we can show is that we can prove lower bounds for homogeneous sigma pi formulas, and we can prove pretty good lower bounds. We can prove lower bounds of the form n to the square root d, okay, for a degree d polynomial in something like n variables. Okay, so this is very, very good. The only thing is that to prove super polynomial lower bounds, I want n to some super constant times square root d. So if I could improve this n to the root d to n to the, I don't know, root d times log n, or n to the root d times log star n, I'd get super polynomial lower bounds. We don't know how to do that, but we know how to match this n to the root d. Okay, and this is not very surprising because the polynomial for which we prove the lower bound is actually a polynomial that has a small circuit. Okay, so we cannot prove that this polynomial does not have small circuits. Okay, and so this polynomial is actually a nice polynomial. It's essentially the polynomial that's complete for algebraic branching programs. It's a so-called iterated matrix multiplication polynomial. So it's just a product of a bunch of matrices where all the entries are distinct variables. Okay, so that's a polynomial. Okay. So what this means is the kind of depth reduction results we've shown in reducing to depth 4, they're sort of tight. We cannot push them any further. And yeah, so we'll have to improve the lower bound in order to prove super polynomial. Okay, so I think that's all I wanted to say about shifted partial derivatives. So I have 5 minutes left, so let me just go through some open questions. And these open questions are more or less related to what I spoke about today. There are many others. So one very sort of nice question which should be attackable, but I don't know why we don't have progress on it, is proving lower bounds for non-commutative VP. Okay, as I said, for non-commutative VBP, for branching programs, we have exponential lower bounds. We have a lot of understanding. And there are also larger classes inside VP for which we have lower bounds. But for some reason, we are not able to prove lower bounds for VP. And again, you could try to follow the sort of two-step procedure here. And it turns out that in some sense, the first step has already been done. So there is work of Rubesh, Vigdison, and Yehudev from 2010, who reduced this question to a kind of a commutative low-depth question. Okay. So I've not written the exact question down here, but it's a very nice problem. It's called the sum of squares problem. It's nothing to do with the other sum of squares from optimization. It's a different sum of squares. So it's a very nice problem about sum of squares identities, and proving lower bounds for that low depth problem will imply exponential lower bounds potentially for non-commutative circuits. Okay, and as I said, it's very sad that we don't have any better lower bounds for non-commutative circuits than we have for commutative circuits. Okay, so it's a very sad state of affairs, and this was sort of there was some explanation given for this recently by Carmosino, Impagliazzo, Lovett, and Mihalin in a very recent paper, where they show that even slightly non-trivial circuit lower bounds, right? So let's say, I don't know what, n to the 1.5 circuit lower bounds, something like that, will in the non-commutative setting immediately imply very, very strong circuit lower bounds. Okay, so you can interpret this either positively or negatively. I would interpret it positively. So now try to prove n to the 1.5 circuit lower bounds, and then we get something very nice. Okay, so that's one question. Another very nice question that sort of we don't know how to answer is whether we can separate these complexity classes in the non-commutative world. We defined formulas, non-commutative algebraic branching programs. It's known that one class is contained inside the other, but we don't know if this containment is strict. Okay, so can you show that? Can you show a separation between the power of algebraic branching programs and the power of algebraic formulas in the non-commutative setting? We expect this kind of separation to be true even in the commutative setting, but the non-commutative setting is a sort of a nice starting point. And this problem has actually a very nice formulation in terms of polynomials. It's just showing that any formula for multiplying D many n by n matrices, where D is, let's say, n, must have super polynomial size. Okay, so it's just proving a lower bound for iterated matrix multiplication. It's a very, very natural question. Sort of, it also reduces a nice small depth question, which probably I won't talk about. But it's kind of the non-commutative algebraic analog of separating NL and NC1. Yeah, so if you would believe NL is different from NC1, maybe this is the right place to start. Okay. All right. So another problem that's sort of a good maybe place to make progress is lower bounds for inhomogeneous sigma pi sigma formulas. So we spoke about homogeneous sigma pi sigma formulas, which are sigma pi sigma formulas where every term has degree bounded by the degree of the final polynomial. But now you can ask about formulas where intermediate terms can compute very high degree polynomials, right? So it's just a sum of products of linear functions, but these individual products can be really, really big. And now somehow things cancel out and you compute a small degree polynomial in a nice way. And potentially this can compute very, very difficult polynomials. So we have next to no lower bounds here. The best lower bound we have is a recent result of Kayal, Saha, and Tavenas, where we get near cubic lower bounds for this model. And it would be nice to improve this. Yeah. And I think I have one more question. And this is sort of a meta-complexity question in algebraic complexity. It's the general question of whether the kinds of techniques that I spoke about and more general techniques in algebraic complexity, can they prove superpolynomial lower bounds at all? Right? So in the setting of Boolean circuits, we have natural proofs and we have many other things that sort of are barriers to what we can accomplish. And recently there has been sort of analogous work in the algebraic setting. So the kinds of rank-based techniques that I spoke about today for proving lower bounds in the second half of my talk, it's known that these cannot prove all the things we might want to prove. So for example, about Waring rank, it's known that these rank-based techniques might not yield the best possible lower bounds. Okay, and there are statements like this. It's a recent work of Efremenko, Gerg, Oliveira, and Vigdison, which proves this. And there have been other results about algebraic versions of natural proofs barriers. It would be nice to sort of strengthen this, try to understand whether these rule out lower bounds for intermediate models of computation, exactly where the barriers lie. Okay, so that's all I have to say. Thank you.
More questions?